Good morning. This is Neil Polhemus. I'm the Director of Development for Stack Graphics here at StatPoint Technologies. I'm very happy. It's my pleasure today to introduce you all to Stack Graphics Centurion version 17. I'm going to be trying to do two things today. I'm going to be trying to show you folks who are currently Stack Graphics users, whether that be Stack Graphics version 16 or 15 or even an older version, all of the new features that we've put into version 17. And also at the same time, for those of you who don't use Stack Graphics, I'm going to show you why we think you should, what's unique about Stack Graphics, how it can be helpful to you in analyzing your data. Okay, now I'm going to show you a few slides to get started, then we're going to go and take a look at the program itself. Stack Graphics Centurion 17 is the 17th version of StatPoint Technologies' statistical analysis and data visualization program for Windows. It started back in the early 80s. It was one of the first statistical packages available for PCs. And as you can tell, we've updated it frequently between then and now. The current version contains more than 230 statistical procedures. If you count all the items on the menu, they're well in excess of 200, around 230. Basically, Stack Graphics Centurion is designed for practitioners, for people who have data and need answers quickly. People who want a powerful tool, but a tool that's easy to use. So many of our users are engineers and scientists. They have a lot of other things on their plates. They may not load Stack Graphics but once a month, and they need to be able to get in and do things quickly. On the other hand, we have folks that use it every day, so there's a real variety of people that use Stack Graphics. Version 17 features 32 new statistical procedures. Version 17 is probably the most significant upgrade we've done in quite a while. There's almost enough in it to have done 2 upgrades, but we didn't. We put it all together in version 17. 32 new statistical procedures, significant enhancements to 20 of the existing procedures, increased data capacity. We've done some work to allow us to analyze larger data sets than we could before. And finally, several new user interface features, things like document passwords, an audit trail, improved graphics editing, recording of videos, zoom and pan, a lot of interesting features. Now, let me actually get into Stack Graphics. What you're looking at now is version 17, the main window, the way it looks when we first come into the program. For those of you who have used Stack Graphics in the past, you'll see that it looks very familiar. That's because a lot of what we've done is actually under the covers. We've had a chance to change a lot of things, add a lot of features here and there that users have suggested over the years. Basically, though, when you load up the program, what you're going to see initially is a data sheet. And in order to get data into Stack Graphics to do some sort of analysis, we need to pull it into that data sheet. Across the top, there's a menu with verbs. We've organized the statistical procedures according to what you want to do with your data. Do you want to describe a set of data? Do you want to compare more than one sample? Do you want to find relationships between variables? Perhaps you want to forecast time series. There's a whole section on statistical process control, a section on DOE, and so forth. What's new in version 17 is the section labeled Statlets. There are 19 new Statlets, and I'll be showing you quite a few of those as I go along. They're statistical procedures which basically open up with a single graphics window doing a particular type of analysis with your data. And as you'll see in a moment, there are controls on a toolbar right on top of the graph to allow you to do and see instantly the effect of various options on the graph that you're looking at. I'll be showing you a handful of these statlets in the next hour. Now, the first thing I do need to do here to do something is to load up some data. So I'm going to go to File, Open Data Source. Now, StackGraphics can pull data from our own data files. We have our own XML type data files where we can store data. On the other hand, we can pull data from other types of files too, Excel files and so forth. To us, we call those external data files. We can do queries against various databases, or we can pull data that you might have copied to the clipboard. I'm going to tell it initially that I'd like to open up an external data file. Now, we can read all sorts of file formats. We can read ASCII files, Excel files, Minitab files, SPSS files, and so forth. The file I want to open up is going to be an Excel file. And when I push the Browse button, it'll give me a list of Excel files in the current data directory. The file I want to pull up is one called Process Data, so I'll tell it I'd like to open Process Data. I'll get to pick the sheet that I want to read, in this case the first sheet, a range of rows. I'll tell it what's at the top of my spreadsheet. Typically you'd have column names at the top of your spreadsheet, but it's possible to have both names and comments or even no header. If I was using some identifier in my Excel file to indicate missing values, I could type that right here, maybe an NA or a 99999 or something like that. Since StackGraphics represents missing values with an empty field, we blank out those missing values for you. Otherwise, I'll just go ahead and press OK. It's going to read the Excel file now into the StackGraphics data sheet. This is some data measuring the strength of a product that's being produced by a manufacturing process. You can see they take samples once a day and measure the strength of the product. Now, whenever I have a new data set, I think the first thing we should do is take a look at it. Well, a good way to take a look at this particular data set is to use one of our new statlets. If I go to statlets, you'll see one of the choices is an interactive histogram. Now, the way the interactive histogram works is it'll display what we call a data input dialog box. It'll ask us what variable we want to look at. In this case, I want to look at strength. And when I do that, it will immediately open up a new window, and in this case, show us a histogram of that particular data. I'm sure you've all seen histograms before. It basically divides the data up into a number of classes and shows us with the height of the bar how many observations are within various classes. Now, what makes the statlets interesting is that the options, as I noted before, are on the toolbar. If I wanted to change the number of classes in the histogram, I can simply go up here and tell it, for example, I want 25 classes or 30 classes. Interactively change the number of classes till I get a display that shows the distribution nicely for me. I can also add a normal curve to the histogram. That would be a curve with the same mean and standard deviation as the data. Okay. Or perhaps I don't think the normal distribution is appropriate. I could try instead a non-parametric density estimator, which is basically a smooth histogram. This particular slider here controls the width of the window that's used to estimate that histogram. And as you can see, I'll pick a smoother width of 25%. And although the lower tail of this distribution does look sort of normal, you see it has definitely a long extended tail to the right-hand side. That's how those statlets work. They're quite interactive. They allow you to do interesting things like that. Now, let me show you some of the new features version 17 in terms of editing a graph like this. Okay. We could always, even in earlier versions, and change, for example, the color of the bars. If I press the right mouse button, go to Graphics Options, I can click on the Fills tab and ask, for example, that all the bars be changed to green. That's something we've been able to do for quite a while. What we have not been able to do is to change the color of just a single bar. In version 17 we can. If we click on the histogram now, go up to what we call the Analysis toolbar, and press this button. It's the Override Attributes button. Okay, I can selectively now change the color of a single bar and make it yellow. That's something that was asked for a long time, and in version 17 we got a chance to actually do that. Now, we've also been able for quite a while to add text to graphs. If I want to add just sort of floating text to my graph, I can always go up and press the appropriate button on the Analysis toolbar. That will give me text that I can then drag to a position on the graph. The thing about text like that, though, is it's at a particular position on the graph, and it will stay there even if, for example, I go to Graphics Options and change the x-axis. Now, suppose I go to Graphics Options, change the x-axis to 180. That text stays right where it is. It's not linked at all to the graph. Well, we have a new feature in version 17 that actually allows you to add objects to any graph. You press this particular button on the Analysis toolbar, and it comes up with an Add Objects dialog box. Now, what sort of objects can I add? Well, one thing I can add is an arrow. For example, I can tell it to give me an arrow at an X position of 200, a Y position of 17. I can tell it to make sure it's a right pointing arrow, and then I can add some text like mode. Okay, when I press apply, you'll see that it's put that arrow at a particular position on the graph. Now, the nice thing about that is if I now rescale the graph, that arrow and text will stay in the same position in plot coordinates. It will always be pointing right at that first bar. Okay. I can also do things like add vertical lines. Let's say I had a spec, for example, at 220. I can tell it to give me a vertical line at 220, and it would do that. I can also ask to just put some particular text at a position. So, for example, I could ask it to put text at 220.5, 17. As far as the properties of the text, I'll tell it, make that reference position at the center left of the text. And let's have it say USL equals 220. Okay. I now say apply, and you can see that that text is put next to the specification limit. Okay. To be able to do these sorts of things really lets me dress up the graphs, make them more informative for presentation purposes. Okay. Some of the other things we've done with graphics which are interesting is, for example, if I press the right mouse button, I can tell it I'd like to save this graph. We've always been able to save graphs in image files. The change here now is you can specify the dots per inch of the target file in which you save it. Okay, we've done that at the request of people who like to put our graphs in various publications, and often the publisher asks for a particular resolution on the graph. Okay, that's new in version 17. Also new in version 17 is something called the stat log. If you go over to the left-hand side of the window here, you'll see what we call the navigation bar. And there is an additional window that's been added to version 17 called the stat log, where you can keep track of everything that's being done. Now, you can actually set up the stat log so it automatically captures all output. Or you can set it up the way I have it, which it means that when you have a graph, if you like it, you push the log button on the analysis toolbar, and it will automatically, you see, copy that graph into the stat log. Now, the stat log is something that you can save as an RTF file at the end of the session and read into Word. Okay, that's another nice feature of version 17. Okay, now there's a few things I'd like to talk about. So let me go back to my slides for a moment, to my PowerPoint presentation. And the next thing I'd like to talk about is changes we've made to data. Okay, obviously, it's very important that we be able to handle data, manipulate data, and so forth, so that you can make good use of all the statistical capabilities we've added to the program. As far as version 17 is concerned, there have been several important data changes. The first change is that the data sheet, the place where I put the data on strength, is now a virtual data sheet. By that I mean it's simply a view of the data. It's not the main repository of the data. What that has done is that's allowed us to save on our use of memory so that we could analyze considerably larger data sets by just making that data sheet virtual. We've also added a new variable that will handle percentage type data, a new column type. We've also added a value labels capability. For those of you who deal with categorical data, we've made it considerably easier to input categorical data, as I'll show you in just a second. And finally, we now allow data to be saved in the Statfolio rather than insisting that you put it in a separate data file. Now, let me illustrate a couple of those things to you, if I can, by going back to StatGraphics. And let me say File New to get myself an empty data sheet. The first thing I'd like to show you is how we use value labels. I'm going to go to the first column, double-click on the header, and tell it I'd like to create a column called Level. In Level, I'm going to want to add the strings, low, medium, and high. In version 16 and earlier versions, you would have needed to make that variable character in order to enter low, medium, and high. Okay? In version 17, you can leave it as a numeric column and push the Value Labels button. The Value Labels button lets you do things like associate the value 1 with the string low, the value 2 with the string medium, and the value 3 with the string high. Okay? Now, what that means is that now I can go ahead and simply enter into the levels column 1, 1, 1, where I want to enter low, 2, 2, 2, instead of entering medium, and 3, 3, 3, where I'd like to enter high. It makes it a lot easier to enter categorical data. In version 16, you would have had to type the words low, medium, and high repetitively. Okay. Likewise, let's look at column 2, and let's make column 2 a variable called usage. I'm going to make it a new data type. In fact, it's going to be a percentage data type. Now, in a percentage data type, if I want to enter a percent, I can just type, for example, 10, 20, 30, 40, 50, 60, 70, 80, 90, and so forth, and it's going to automatically put the percentage in for me. Okay? That's convenient. Now, let's do a quick plot of this data to show you what it would look like. I'm going to go to Plot, Scatter Plots, XY Plot, and ask for it to plot usage versus level. Okay, what you can see is that it's plotted the usage data as a percentage on the y-axis, and on the x-axis, in place of the numbers 1, 2, and 3, it's put low, medium, and high. That would be true in any table, any graph throughout the system. That categorical variable now, the numbers 1, 2, and 3 will appear as their labels. Okay. Now, one other important addition to StatGraphics version 17 is the ability to save this data as part of the StatFolio. If I wanted to save this data in StatGraphics version 16, I'd have to create a separate data file. Here I can just say File, Save As, Save StatFolio As. Now, for those of you who've not used StatGraphics before, the StatFolio is our main document. It saves all the analysis windows that we create. It can now also save the data. So I'll tell it, for example, I want to save the StatFolio as File 4. Then if I clear off everything, go back to an empty data sheet, and tell it I'd like to reload that StatFolio, you will notice that it's reloaded not only the XY plot, it's also reloaded the data, and you can see the header of the data sheet is in StatFolio. So that particular data, rather than being saved in a separate data file, okay, has actually been saved in the StatFolio. You can still access, of course, external data files, as I did with process data, and save data in separate data files if you want to access them by many StatFolios. But for small data sets like this, it's just very convenient now to save the data together with the StatFolio. Okay. Well, that's a little bit about what we've done in terms of data changes in StatGraphics. We've also made quite a number of changes to the statistical process control capabilities. We've added in version 17 several new acceptance sampling plans. We've added acceptance sampling plans based on ANSI Z1.4 standards, which used to be called Military Standard 105E. We've added an ANSI Z1.9. 1.4 is for attributes. 1.9 is for variable data. And we've also added the newest DoD standard, which is MIL Standard 1916. That works for either attributes or variables. We've added some new control charts to the program. We've added T-charts and G-charts to monitor rare events. That would be things like the occurrence of infections in a hospital. We've also added U' and P' charts to handle over-dispersed counts. These are sometimes called Laney control charts, and they're very useful if you're counting nonconformities, but your sample sizes are quite large. We've added to StatGraphics a statlet that implements reliability demonstration test plans. These are demonstrations where you can show that your product has some stated reliability. For example, that 90% of your product will still be working after 2,000 hours. The test plans will determine for you how many items you need to test, how long you need to test them in order to make those sorts of statements. And finally, we've added a new process capability statlet. Now let's go back to StatGraphics. Let's clear off what we've done so far. And let's call back that Excel file with the process data. Now, In version 16, I would have had to go back through the same process of opening that Excel file. In version 17, you can simply go down to recent data files. And in addition to remembering the recent StatGraphics data files, it now remembers the recent Excel files. So I can just click down there on Process Data. It will reread that Excel file for me. Now, I'd like to take this process data and do what's called a process capability analysis. That will mean comparing this data to a specification. There's a new statlet that does this really nicely for me. It's the process capability analysis statlet. The way it works is you put in a column for the data. That's a column called strength. And give it a specification limit. For example, let's assume that there is a 220 PSI specification as the upper limit for strength. Okay? If I press OK, what's going to happen is a statlet will open. And like the interactive histogram, this statlet has a basic graph, and it also has a lot of controls where I can change different options. Right now, what it's done is it showed me a histogram of my data. It showed me a normal curve with the same mean and standard deviation as the data. The tall vertical line is at the spec. The shorter vertical lines are at the mean, plus and minus 3 standard deviations. Now you see on the toolbar that if I want, I could change from sigma limits to statistical tolerance limits. And what it's done by default is created what are called 95-90 tolerance limits. They give me limits within which I can be 95% certain that at least 90% of my data, my population, will actually lie. Not my data, actually the population from which I've taken the sample of the data. Now, I can change the characteristics of this. For example, I think I'll move the limits out and make them 95-99% limits. They're now limits that I'm 95% certain will contain 99% of my data. I can also make them one-sided. That might make some sense. Since I only have a one-sided specification limit, I might want a one-sided upper tolerance limit. I can now claim with 95% confidence that at least 99% of my product lies below 219.55. Okay, since the upper spec limit was 220, one way of assuring capability is to do the 95-99 tolerance limit, and hopefully you'll see what you see here, that the upper tolerance bound will be less than the upper spec. Now, at the same time, you can see in the right margin of the graph some interesting statistics. You see a normality p-value from a Shapiro-Wilks test, a distribution fitting p-value from a Kolmogorov-Smirnov test. You see both short-term and long-term capability indices, CPK, PPK, and defects per million. Defects per million estimates how many items per million I'm producing that are likely to be above that upper spec. Now, to assume a normal distribution, unfortunately, both of these p-values, both the Shapiro-Wilk and the Kolmogorov-Smirnov statistics, both p-values should be greater than 0.05. They're not greater than 0.05, which means that the normal distribution actually is not a good model for this data. Well, there are a couple things I can typically do about that. One thing I can do is I can try what's called a power transformation of the data. And you see up here on the toolbar a slider that controls the power. Often, even though the original data may not follow a normal distribution, you can find a power transformation that makes it approximately normal. And in fact, in this case, if I were to take my data, raise it to the -5 power, you'd see that both the Shapiro-Wilk p-value and the Kolmogorov-Smirnov p-value are well above 5%, indicating that I could reasonably believe that in the metric strength raised to the -5 power, a normal distribution might be appropriate. Well, if that is the case, what we would typically do is transform the data, create our tolerance limits, and then transform everything back to the original units. And unfortunately, you see, if I were to do that, my upper tolerance bound is now above the upper specification limit. I say unfortunately because if you look at things like defects per million, you see that they're quite a bit greater than they were when I assumed a normal distribution. However, since the data were not normal, it's much more accurate to do something like that transformation. Okay. On the other hand, if I didn't want to do that, I could also just come back to a power of 1, okay, and pick, for example, some other distribution. There's lots of other distributions that could be appropriate. I happen to know for this data that the largest extreme value distribution is actually a good one to use. The nice thing you can see about the statlet is you can do all of this interaction dynamically on the graph. Okay. Let me show you a couple other things that we've added in the SPC section. I did mention that we added a reliability demonstration test plan. Here it is. The reliability demonstration test plan allows me to demonstrate that my product meets some claim. For example, I might like to claim that 90% of my product will still be working after, let's say, 2,000 hours. It might be a claim that you do in a warranty or something like that. Okay. To make that claim, you typically need to assume some sort of a distribution. Most common distribution for lifetime data is a Weibull distribution. Now, what the statlet will do is it will figure out for you, if you want to make that claim, that 90% of your product will still be working after 2,000 hours, it will figure out for you either how many units you need to test or how long you need to test them for. For example, I can tell it I want to test 20 units, and it will tell me, well, if you do that, you'll need to test 20 units for 2,528 hours. If you see no failures, then you can claim 90% reliability at 2,000 hours. If you say, Neil, I can't run my test for 2,528 hours, you can instead fix the test duration. And if you tell me, for example, you can only run for 500 hours, I'll tell you that's fine. You can run for 500 hours, but you need to test 228 units. And again, if 228 units show no failures after 500 hours, you can claim 90% reliability at 2,000 hours. That's the reliability demonstration test plan, and it's quite useful for people who need to demonstrate product reliability. We've also added to the SPC section new procedures for doing acceptance sampling. As I said, we've added various ANSI and military standards. Now, just to quickly show you how these procedures work, suppose I wanted to implement the DoD's latest standard, which is Military Standard 1916. A dialog box will come up. It will ask me, okay, you want to draw a sample from a lot, right? A lot or a batch or whatever. What size is that lot? Well, let's suppose I have a lot of 1,000 items. Okay, there's a range in the Military Standard 1916 that contains 1,000. You tell it what verification level you want to operate at. Level 4 is the default. You tell it whether you want to do reduced, normal, or tightened inspection. I'll just say normal. And when you press OK, it will figure out for you how many items you need to sample from that lot of 1,000. In fact, it says you need to take 96 samples from that lot of 1,000 items. If you see 0 non-conforming items, you can accept the lot. If you see 1 or more non-conforming items, you need to reject the lot. Either reject it or subject it to 100% inspection. Military Standard 1916 plans are what are called zero defect acceptance sampling plans. They all require you to see no defective or non-conforming items to accept the lot. There's also an alternative sampling plan. If rather than waiting until you have the entire lot produced in order to begin inspecting it, there are what are called continuous sampling plans. And it says that I could, instead of waiting till the end of the lot, start my inspection immediately as I start producing the items. And there's a screening phase, and it says I would need to inspect 372 items. And then if I saw no defects, I could go into the sampling phase where I inspect 1 out of 17 items. Okay. The important thing here is that we have added to StackGraphics version 17 some new acceptance sampling plans. Okay. Those are new features we've added in the areas of SPC. We've also added a lot in the area of statistical modeling. We've added 2 new procedures for handling repeated measures designs, for doing the repeated measures ANOVA, including a sphericity test and adjustments for if there is not sphericity present. We've added factorability tests in both the principal components and factor analysis procedures, particularly the Kaiser-Meyer-Olkin measure of sampling adequacy. We've added new statlets to do curve fitting and surface fitting. We've added a new item reliability analysis. The key statistic there is something called Cronbach's alpha. We've added to the multiple samples comparison procedure methods for handling heterogeneous samples. Those are samples which have different levels of variability. Included here are the Welsh and Brown-Forsyth tests, the Gaines-Howell post-hoc comparisons. We've also created a new power transformations statlet, a sample size determination statlet, which will determine the sample sizes you should collect for estimating certain things, including a correlation coefficient. And also a very interesting new procedure called kriging. Now, the procedure I'd like to show you here is the kriging procedure. This is actually brand new to StackGraphics. You won't find it in too many other statistical programs, but it's actually quite useful. The file I want to open up to show you kriging is something called Broom's Barn. Now, Broom's Barn is a location at the Rothamsted Agricultural Center in Rothamsted, England. And it's a famous data set where they actually took samples of a product at different, not samples of a product, they took soil samples at different locations within a field. What we have in this data set is the results of samples taken at different locations. East and north here are columns that show me the location in the field at which the sample was taken. Then we have at each location the amount of potassium, the pH, and the amount of phosphorus. The idea of kriging is to model the distribution of a variable like potassium throughout the field. Okay, not only at places where we've collected data, but also at places where we've not collected data. Now, there's a real nice statlet that will do this. I'm going to go to Statlets and tell it I'd like to do kriging. Now, what I need to do is I need to specify several things. First off, I need to tell it what variable I'd like to model. And in this case, I'm going to model the log of potassium. Okay. X1 and X2 want columns that tell me where in the field each of these samples came from, so I'll put those in the X1 and X2 fields. And then I have a couple places where I can put boundary indicators so it can actually plot the field for me. Okay. Now, what's going to happen is this will open up a brand new statlet. And initially, it's going to show me the data. Now, if I tilt it all the way like this, you can see the locations throughout the field at which the soil samples were taken. They took it basically over a grid, a whole bunch of different locations on a grid, except there were places they couldn't take samples. There were certain swampy areas like here where they couldn't take samples. There was a road over here. I think there was a building of some sort over here. What we'd like to do, though, is get a model of how, in this case, the log of potassium distributes itself across the field. And if I tilt it back like this, you can see vertically what the log of potassium was at all of those locations. Now, there's a lot to kriging. I can't explain the whole thing. However, there are a number of different steps. The first step, typically when you're doing kriging, is to estimate something called the variogram. The variogram shows how the spatial dependence of points varies as a function of the distance between the points. Okay, and typically what you do is you try, when you're doing kriging, to come up with a nice model that describes, at least for short distances, relatively short distances, how the spatial dependence varies. And what we've done in this case is we've fit an exponential model which shows that the spatial dependence, and what you see on the y-axis is actually the variance of the difference between points separated by particular lags. There's what's called a nugget at the beginning, which is the variance between observations taken at the same position. And then as the points get farther and farther apart, you see that the variance rises exponentially until it reaches an asymptotic sill. Okay. Well, you can use this variogram now to help map out the log potassium throughout the field. Okay? And I can change the maximum radius here to get a little bit more detail. What you have here, though, is a response map. The blue sections are areas where the log potassium is low. This red section here is a hot spot in the field where the log of potassium is high. You can actually see that also, if you prefer, in 3 dimensions. And it gives me a nice surface plot. Now you can see that one sharp peak where the potassium was high, and you can see in the back that low area where the potassium was quite low. Okay. Very nice, I think, interactive statlet that lets you apply a relatively complicated statistical procedure. Okay. All right. Well, I wanted to show that to you. We've also added some things in the area of time series analysis. We've added something called an exponential smoothing statlet. We've added an open high-low closed candlestick plot to plot stock prices. We've added some dynamic visualizers, which I'll be showing a little later. Okay. First thing I thought I'd show you actually was an exponential smoother. So let me go back to StatGraphics. Let's close off this particular data file. I've got another data file that will interest those of you who deal with financial data, and labor-related data and so forth. It's data on the unemployment rate monthly in the United States. It's a file called unemployment rate. For every month during the entire century, I've recorded what the adjusted and unadjusted employment rates were. As you go down here, you'll see that the data go all the way through the end of 2014, and the adjusted unemployment rate was actually 5.8% back in November. Let's suppose I'd like to take this data and forecast it. A common way to forecast data is by using something called exponential smoothing. Exponential smoothing lets me take a set of data and apply various types of smoothers to it to forecast what's likely to happen in the future. Now, this is a statlet, so I can change some of my options, such as the number of forecasts I'm going to make, using controls on the toolbar. It started by doing simple exponential smoothing. Well, simple exponential smoothing, unfortunately, gives me a horizontal forecast function, not particularly effective on this particular data. Incidentally, the points here are the actual unemployment rates. The smooth values are the results of the smoother. Exponential smoothing, by the way, has certain smoothing parameters. In the case of simple exponential smoothing, it has something called alpha. I can change alpha, and as I change it, watch some of these statistics. You see here statistics such as the root mean squared error, the mean absolute percentage error, and so forth. And you can see as I change the smoothing parameters, particularly as I increase it here, that things like the mean absolute percentage error are getting smaller. The smoothers doing a better job mimicking the data, but still not doing a very good forecast. If you want to do a good forecast for the unemployment rate, you really need to use something like Holt's linear smoothing. Holt's linear smoothing has two parameters. It has an alpha and a beta. It's a two-pass smoother. What you see at the end of the data set here is you see that the forecast function from Holt's exponential smoothing is a line. It's linear, in this case downward sloping. You also see 95% confidence limits. Well, there's an optimize button on the toolbar. If I hit optimize, it'll actually find the values of alpha and beta that minimize the minimum absolute percentage error. And if I say minimize, it says you should use a smoother of 0.93 for alpha and 0.23 for beta. And it does suggest that over the next several months, unemployment in the United States will go down. However, you can see from the 95% confidence limits that it's not too certain about that. It's within the 95% limits, the possibility that, in fact, it could turn around and go back up. Tough data to forecast, but at least the exponential smoother makes it easy. Okay. What else have we added to Stack Graphics? Well, we've also added some new features in the areas of design of experiments. We've added new screening designs based on three-level fractional factorials. We've increased the number of response variables in our design of experiments section from 16 to 32. We've improved the ternary plots when we're dealing with mixture components. And most importantly, we've added something called computer-generated designs. Computer-generated designs are designs that will optimize either the A efficiency, the D efficiency, the G efficiency, or the I efficiency of your experiment. They're particularly helpful when you have constraints on the factors. Now, I thought I'd show you here an example of our new designed experiments. It's an example from a book by Goose and Jones. called Optimal Design of Experiments, a Case Study Approach. In their experiment, what the analysts wanted to do is they wanted to maximize the yield of their process. There were two factors that could be changed. It was a manufacturing process of some sort. One factor was time, which they figured they could vary between 320 and 720 seconds. A second factor was temperature. It could be varied anywhere between 520K and 550K. Okay. Now, in version 16, if you wanted to set up that sort of experiment, you would have had to have chosen something like a 3-level factorial or a central composite design or a box Bankin design or something like that. Okay. Problem here, though, is that there are constraints on the factors. Actually, constraints on the experimental region. It turns out in this case that 0.3 times time plus temperature had to be at least 539.8. 0.909 times time plus temperature needed to be less than 587.8. If you read Guza and Jones, you'll see that what they came up with these constraints to eliminate the bottom left corner of the experimental region and the upper right-hand corner. Okay. I want to show you how we can use the new features in version 17 to set up a design for this situation. Okay. So to do that, I'm going to go back to StackGraphics. I'm going to close off what I've been doing so far. Okay. Now, to set up an experiment in StackGraphics, it's similar to version 16. You go to DOE and invoke the Experimental Design Wizard. The Experimental Design Wizard will bring up a toolbar and take you through a 12-step process where you can create and analyze a design. Step 1 is where you define your responses. And in this case, we have yield. It's in grams. And my goal is to maximize the mean yield. The other fields over here we don't need to use since we only have one response. Step 2 is where I define the experimental factors. Now, in this case, there are two experimental factors. There's time in seconds. It's a continuous variable. It ranges between 320 and 720 seconds. The second variable is temperature. It's in degrees Kelvin. It's continuous. It can range between 520 and 550. Okay. That's the same as it was in version 16. Where things become a little bit different is in step 3. Here, when I press the Options button to set up a design, I'll have a new choice. It's called Computer Generated. That's telling it I want to use the new computer-generated facilities. I'll go ahead and press OK. What's also new is this button down here labeled Constraints. This is where I go to add constraints. This is where I tell it that if I take 0.03 times time plus temperature, that has to be greater or equal to 539.8. Okay? And that will put up here a constraint for me. I also tell it that if I take 0.09 times time plus temperature, that has to be less than or equal to 587.8. Okay? So I've specified two constraints that need to be met. I'll then press OK and OK, and you can see it's selected a computer-generated design, and here are the constraints. Step 4 is where I select the model, and a quadratic model is going to be good for this case. Step 5 is where we actually generate the design. Step 5 brings up a dialog box. that lets me choose between an I-optimal design, a D-optimal design, an A-optimal design, or a G-optimal design. Okay. I have a choice of displaying either original units or coded units. And I also need to indicate how many runs I want to perform. Well, following Goose and Jones, they told it to generate a design with 13 runs plus 2 replicates. That would be 13 different combinations of time and temperature, and then replicate 2 of those. When I press the Create button, it now creates what's called a D-optimal design. Okay, and when I press OK, it will put those runs into the data sheet. That is a 15-run D-optimal design in that constrained region. Now, to show you it is in the constrained region, I'm going to go to step 6 and ask it to plot out the design points. Okay, here you can see in the space of time and temperature the points that it generated. These are points at which it wants you to do the experiments. And you can see the constraints. There's one constraint running down through here that says, please don't run down in the lower left corner. There's another constraint up here that said, don't run in this upper right corner. So it has generated an experimental design over that constrained region. That you could not do in version 16, but it's really quite easy to do in version 17. Okay, well that's some of the features we've added to the design of experiments section. The last set of features I want to show you have to do with data visualization. We've spent a lot of time in version 17 essentially going back to our roots. StatGraphics was initially created to allow users to display data in many different ways. Okay, back when we started, it was at the very beginning of the PC, where the ability to generate graphs on the screen was quite new. And we called it StatGraphics because we combined a lot of the numerical statistics with a lot of graphical things. The computers have gotten so fast these days that there are a lot of very interesting things now that you can do that you couldn't do back then. And we've spent quite a bit of time adding new visualization features to StatGraphics. I showed you one already. That was the interactive histogram. Another procedure, one I am going to show you, is a bivariate density. We've added a choreogram for displaying correlation matrices. We've added one-dimensional, two-dimensional, and three-dimensional dynamic visualizers. We've added a multivariate visualizer. We've improved our demographic maps. And we've added a new feature that I call the deviation dashboard. Okay. Now, let me take a few minutes and show you these. I see everyone's still with me that signed on at the beginning, so I will beg your indulgence and take a few minutes and show you some of these other interesting visualization features, if you don't mind. Let me close off what we've done so far, okay? And now open up a new file, one we haven't looked at, but a very interesting file. It has data from the World Bank. Okay? The data on the World Bank has data for 188 countries throughout the world. It has data from 1961 through 2009, I believe. We know for every country and every year the population density, the rural population, the percent of females living in the country, age dependency ratio, life expectancies, fertility rates, all sorts of interesting demographics about those countries. What I'd like to show you first is under Statlets. It's called the bivariate density statlet. The bivariate density stat, it will let me take two columns. I'm going to take fertility rate. That's the number of children per woman in a particular country, and plot it versus life expectancy. And I'm going to do it down here in the select field for year equals 1961 to begin with. What the bivariate density stat it will do is it will take the data and display in a number of different formats the joint distribution of those two variables. What you see by default here is a three-dimensional histogram. It's showing the joint distribution of fertility rate and life expectancy. And what you see back in 1961, remember this was 1961, are two groups of countries. You're seeing a bunch of countries here with fertility rates between 2 and 4, 2 to 4 children per woman, and relatively long life expectancy, between about 60 and 70 years. You see a whole nother group of countries with fertility rates between 6 and 8, and considerably shorter life expectancies. Now, that's a frequency histogram. You can also show it as a normal distribution, a bivariate normal distribution, although I don't think things are particularly normal. Or you can use what's called a non-parametric density estimator. A non-parametric density estimator will estimate the joint distribution using a smoother similar to the way we estimated the density in that interactive histogram. And if I adjust the smoothing width here, you'll see that this particular data definitely has a couple modes. It has a mode here, where that first group of countries was, and it has a mode here. That's the second group of countries. Okay. Now you can see this incidentally as a contour plot or a surface plot. As a contour plot, you can see that there are two primary areas where there are a lot of observations, or you can see it as a three-dimensional plot. Now I can also go back to the data input dialog box and change it to 2009, and you'll see quite a bit of difference in 2009. By 2009, the countries that had high fertility rates have now changed, and a lot of them moved into the group with lower fertility rates and higher life expectancies. Now, we also have a real nice visualizer that can visualize this data dynamically. I'm going to go back to Statlets again, and this time choose the 2D dynamic visualizer. I'm going to take those same variables. I'm going to take life expectancy, and I'm going to take fertility rate. I'm going to slice by year and identify by country code. I'm also going to use region of the world to color the points. This will all make sense when you see it in a second. Here it is. This is what we call the two-dimensional dynamic visualizer. And I'm going to go to Toolbar and incidentally reduce the text just a little bit. Okay. What you see here is a scatter plot. Life expectancy is on the y-axis. Fertility is on the x-axis. Okay, you see the group of countries up here, and now you see that most of those countries are from Europe or North America. Down here with lower life expectancies, higher fertility rates are sub-Saharan Africa, a fair amount of South America, although some of the South America is also up here. Now, what makes this interesting is I have a control bar here where I can change the year. I can move the year dynamically from 1961 up to 2009 to see how things have changed. Or I can just push this arrow and have it move by itself. And now you can see that between the years 1961 and 2009, the world has moved up toward that upper left-hand corner. Okay, fertility rates have come down pretty consistently, and life expectancy has gone back up. A couple other interesting things I can do. I can press the right mouse button. I can go to Analysis Options, and I can ask it to leave breadcrumbs for the bubbles. We call this actually a bubble plot. And now if I push the right arrow, it's going to leave breadcrumbs, so you can track where those observations have come from. Okay. You can see that for many of them, the fertility rate actually increased at first, but now they've all moved toward levels of lower fertility. I can also put labels on particular points. If I go back to Analysis Options, I can tell it to label selected identifiers. And two interesting points to label are China and Vietnam. Okay? Now what you're going to see, let's see, did I actually tell it to label the selected identifiers? I believe I did. Oh yeah, there they are. Here's China right about here. I need to maybe increase the text a little bit. There we go. Here's China right here. Here's Vietnam right here. Watch China and Vietnam as time evolves. China early in the 70s makes a very fast move up toward the upper left. Vietnam's a little bit later, back in the 80s, but by the mid-90s, China and Vietnam are now up in the upper left corner, lower fertility rates, higher life expectancies. Okay, that's an interesting plot. That's called the 2D dynamic visualizer. Now, another plot that people like a lot that I can do on the same data is something called a choregram. I'm going to go to Describe Numeric Data Multiple Variable Analysis. Okay, and this time what I'm going to do is I'm going to pick about 12 different variables. I'm going to pick population density, rural population, female percentage, age dependency ratio, life expectancy. I'll pick those. I'll pick the difference between females and males, fertility rate, infant mortality, trade, GDP, central government debt, consumer price inflation, real interest rate, unemployment. Put those all in here. When I press OK, it'll ask what I want to analyze. I'll tell it take, oh wait, I need to go back for a moment. I also wanted to do this only for 2009, so I'm going to tell it use 2009. Now, there's a lot of data in here. I just want to look at a particular year. I'm going to tell it if there's missing values to use all the data. And what I'm particularly interested in looking at is something called the correlation plot. This is the correlation plot or core plot. And I'm going to do a couple things here. I'm going to reduce the text a little bit, and I'm going to drag it up a little bit. Okay? What you're seeing here is a correlation matrix. It has the correlation between all pairs of variables, all of these 12 variables, and at any location, row and column, you have a correlation coefficient. Now, it's color-coded the cell from dark blue if it's a strong negative correlation to dark red if it's a strong positive correlation. Well, it's a scatter at first. If I go to pane options, however, I can ask to sort it by the first eigenvector, the first principal component. And this helps interpretation a lot because this will put like variables together. You'll now see that there are several variables with a lot of dark red. Infant mortality, fertility, age dependency ratio, all positively correlated with each other. Down in the bottom, you see also some fairly strong correlation between GDP and life expectancy. Here you see some blue, life expectancy and infant mortality having a very strong negative correlation, as you might expect. Some of these correlations are not statistically significant. I can also have it replace with an X any correlations that are not statistically significant. The nice thing about viewing this correlation matrix is you can see a lot very easily that's difficult if you were just looking at a table. So if you have a lot of response variables and you want to start searching for correlations amongst them, the correlation coefficient is a real nice way to do that. Okay. One more plot to show you, and then I'm going to stop for a few questions. And this will be some of our demographic maps. I'm going to clear off this particular data set and now open up one more data set. This data set is called Western Hemisphere. It's actually a subset of the World Bank data set with data just for the Western Hemisphere. Now, if I go to Statlets and go down to, where is it? There it is, Demographic Map Visualization. You'll see that this procedure will allow me to take a column like rural population and display it on a map. Actually slice it by year, identify it by color code, but then plot it on a map. In version 17, we can plot data on any map that's defined by what's called a BNA boundary file. We have a boundary file for the U.S., we have a boundary file for France, we have one for the Americas, which is the one I want to choose. There are lots of other boundary files, though, on the Internet, and if you can find a BNA file for an area you want to plot, you can now plot it using StatGraphics. What this is going to do is this is going to make a plot for me. Okay, and I'm going to resize this a little bit. Okay, so I get the aspect ratio a little bit better. I'm also going to change the scaling a little bit. 0 to 75 is a little bit better, so you can better see what's going on. Okay, what we have here is a map of every country in the Western Hemisphere in 1961. We have color-coded each country according to the percentage of the population that lives in rural areas. Countries that are red have 75% or more of the people living in rural areas. Okay, and as it gets bluer, the rural percentage is smaller. You can see back in 1961, there were a number of countries, particularly in South America, with fairly high rural populations. Well, like the visualizer, I can let time run, and you'll now see things change as we go through the 70s and the 80s, and particularly as we get into the 90s and into the 21st centuries. You can see the countries becoming much less red. There's a lot more blue showing up as people move out of the rural areas into urban areas. Okay. That's called the Demographic Map Visualizer, which I believe is quite interesting. Well, I actually lied to you. I told you that was the last thing I was going to show you. There's one other thing I need to show you, too. It's the deviation dashboard. Since you're all still here, give me 2 more minutes. I'll show you the deviation dashboard. Okay? The deviation dashboard was originally designed to plot multiple control charts. But I found out it works really well on any data that's multiple columns measured over time. The data set here is actually a data set called the Gulf of Maine. It has fish counts. Fish counts at various locations, 13 different locations actually in the Gulf of Maine between the years 1963 and 2003. If I go to Statlet's deviation dashboard right here, I can take these multiple time series and plot them by year. And what it will do is it will create for me a multiple bar chart initially. Now let me turn the labels a little bit. Let me reduce the text size so that everything fits nicely. What you're seeing here actually for 1963 is fish counts at 13 locations in the Gulf of Maine. They're standardized so that the bars show you how many standard deviations the fish counts were away from their long-term mean. If they make it to these red lines, it means they're 3 standard deviations away from the mean. I've color-coded the bars. If they're green, dark green, they're within 1 sigma. If they're light green, they're between 1 and 2 sigma. You'll also see yellow and red, yellow from 2 to 3 sigma, and red if it goes beyond 3 sigma. I'm going to let time run now and go through the years, and you'll see some definite changes. Oops, I saw some red. You can see that during most years they stayed within the 3 sigma limits, sort of bouncing around like you would expect a random series to do. But back there around, I think it was 78, was it? Let me go back. There we go. To 1979, actually, there were 1, 2, 3, 4 locations in the Gulf of Maine where the fish counts were above their upper 3 sigma limits. I call that the deviation dashboard. I'm showing you the extent of the deviations over time. There's actually 2 formats for it. If you don't like my bar charts, you can do connected line charts instead. This is what I originally had in mind when I designed it for multiple control charts, so that you could monitor multiple variables over time and determine which ones at any point in time were beyond the 3 sigma limits. Okay, and you can see back here in 1978-79, for some reason at certain locations in the Gulf of Maine, the fish counts got very large. Okay, well, I appreciate your staying around a little longer. It looks like everyone stayed. I hope that means it was interesting to you. There's a huge amount in version 17. Like I said, it's one of the largest releases we've ever done, the most significant updates we've ever done. 32 new procedures, enhancements to 20 other procedures, all sorts of user interface features that people have asked for. Even simple things, incidentally, like changing the width of this navigation bar. I didn't show you that, but what we tried to do with version 17 is implement a lot of requests that people gave us over the years. All right, well, let me look at any comments that have been sent in. One thing before I do talk about the comments. There's a lot more to learn if you go to our website. Okay? We have a brand new website. It's at www.stackgraphics.com. Same URL, but a different website with lots of information about Stack Graphics Centurion version 17. You'll also see there about 50 videos that I've done about new features in Stack Graphics version 17. There's over 5 hours of videos that I've recorded on each of these features that I've showed you today, obviously more detail. So I hope you'll write down that particular link. We've also started a blog. If you go to our home page at www.stackgraphics.com, you'll see a button that says Visit Our Blog near the bottom of the home page. I'm going to be posting the video of this webinar on that blog, and if you do have comments, we would love for you to go and find the blog for this webinar and add some comments. I'm going to be monitoring that particular blog, and we'll respond to any comments. And as I said, every time we come out with a new version, most of what we put in were things that people suggested or asked for along the way. So if you would, please go to our blog. Now, let me see if we did have any questions. I don't think we had too many questions. There was one question early on. It says, if you're on a network, can you access the same Statfolio file on any computer in that network? The answer is an absolute yes, you certainly can. We do have a network version of StatGraphics. Basically, we have a standalone version and a network version. Regardless of which version you're using, you can go and open up a data file anywhere as long as people haven't put passwords on it. One thing I didn't show you, and maybe that's what this particular question was getting at, is that we have added the ability, if I go to edit Statfolio passwords, to protect your Statfolios now by putting a password on them. You can put an owner password on it so that no one can open it without knowing the password. You can also add, though, a user password and allow users to only do specific things. Okay, if you don't put a password on your Statfolio, then anybody can open it from anywhere. And you can easily go and pull the Statfolio off a network regardless of where you happen to be. If you do protect it with a password, you could still open it from a network, but whoever tried to open it would have to know the password. Okay, that is one new feature. I didn't mention it. Maybe I mentioned it in one of my lists, but that would be the only restriction on opening Statfolios. Okay, there's another question, Cronbach's alpha. Okay, that's what we used in the item reliability analysis. It's asked if that is for ordinal data and what we do with missing values. Well, I know the answer to the first. Yes, it is for ordinal data. Typically, Cronbach's alpha is used to look at survey data, where you might ask the user to respond either, you give them a statement. Statistics is fun. Tell me, how do you feel about that statement? Disagree strongly, disagree, agree strongly, or no opinion. Okay? There's a rank order to the responses. Cronbach's alpha will look at various questions on a survey and tell you if there are particular questions which are not consistent with the rest. I mean, given that they're trying to get at some particular feeling on the part of the people that took the survey, Cronbach's alpha basically is measuring consistency amongst the responses to the different questions. What do you do with missing data? I don't know that offhand. I'm actually about to record, though, a video that I'm going to put on the video page, the instructions video page. Where is it? There it is. Having to do with that item. It's in the item reliability analysis. And I will be sure to look up and then tell you as part of that video what we do with missing values, because I simply don't know offhand, off the top of my head. But I will look for it, so if you would, give me a day or two to post it. It takes a while to create all these videos, but I will find out what we do with missing values when we do Cronbach's alpha. Okay. Someone was also indicating that they could not stay for the entire presentation. Will we post the slides? Yes, I'm going to post both the slides and the recorded webinar so that you can either listen to the webinar again That's unlikely, but maybe you have colleagues that would be interested in listening to the webinar. If you would point them to the recorded webinar. I will, though, put the slides up so that you could look briefly at what I talked about. Okay. Another question came in, what export formats do we have for graphics, and what's the maximum dots per inch? Well, let me see. If you're in Stack Graphics and you have a graph, and you press the right mouse button and say, I want to save the graph, you can pick a dots per inch. I don't know what the maximum is, to be honest. You'll have to either try that, or I can check that for you too. I'll do a little research, see if I can find out what it is. I'm not sure that there is necessarily a maximum. I know the graph's going to get bigger, the file's going to get bigger if you ask for a higher resolution. As far as what image formats we can save it in, we can save it as a Windows meta file, a JPEG file, a TIFF file, a PNG file, a bitmap, or a GIF file. Those are the options that we can currently save it in. Okay. Someone also just put in a question asking whether we can evaluate algebraic expressions in text boxes. Well, the answer to that is yes. For example, let me open up a file that I look at a lot, which is, where is it? It's called 93 Cars. It's a file that has various information about automobiles, including, for example, miles per gallon in highway driving and miles per gallon in city driving. Whenever I start a procedure, let's say I do an interactive histogram, in addition to putting in things like miles per gallon in highway driving, I can type algebraic expressions. So I could type, for example, miles per gallon in highway driving divided by miles per gallon in city driving. And now it will do an analysis on that particular ratio. Okay. You can you can put in any of those dialog boxes algebraic expressions involving one or more of the data variables. Okay, there are also operators like log that I could put around the whole thing if I wanted to take the natural logarithm. I don't know that that would mean much in this case, but yes, algebraic expressions can certainly be typed where it would normally expect numeric input. Okay. I don't at the moment see any other questions. Please, if you do have more questions, go to our blog. There it is. I will be posting a blog for this particular webinar. If you do have questions, I will definitely be willing to answer those. Oh, I see one last question came in. It says, can the year transition be output to an AVI or some other format of video? Well, there's another thing I didn't show you, wasn't it? I didn't show you how in Stack Graphics you can actually record a video. But yes, you can. If I have some sort of a video, and maybe I had, for example, the World Bank, there it is, and I was doing maybe a 2D dynamic visualizer looking at life expectancy as a function of fertility, sliced by year, identified by country code, and I think I had color being the region. Okay, what I can do, there's a new button on the toolbar looks like a piece of film that lets me record a video. Okay, it brings up a little dialog box, and if I push start, it will start recording a video. Actually, it'll ask me what compression I want to use, but then it will start recording a video. And I can just let the video go. There it goes. It's recording that right now. I'll stop it when I get to the end. I'll tell it to stop, and then I'll tell it to please save that video, and I'll call it my video, for example. Okay? So it's now created a video. That video, incidentally, I can put into PowerPoint. Okay, let me go back to my PowerPoint presentation. I'm going to tell it to create a new slide. And let's just make the layout of this slide title only. Okay, call this my video. And then I'm going to tell it to insert a video from file. Well, I actually saved this one. I think it was back in C, Data, Webinar. Maybe that wasn't where I saved it. Did I just? Oh no, I know. I had opened up something from Doc Data 17. There it is. There's my video right there. Okay, so here it is in my PowerPoint slide. And now if I push Shift F5, I should be able to click on the video and have it play. There it goes. So the answer is yes, you can record videos. They're recorded as AVI files and save them into PowerPoint slides or whatever you want to do with it. I'm busy looking at the next question. So yes, that's a nice new feature in version 17. There's another question here. It says, Neil kept adjusting the font size in the graphs. Is it possible to set it so that you don't have to do that? There is. If you're in Stat Graphics, let me get back to Stat Graphics. Let me get rid of this. You can always push the right mouse button, go to Graphics Options, and change things like the size of the fonts. If I say, for example, I want to change all the fonts, I could reduce the size of all the fonts. After I did that, I could then push the Profile button and save away my new settings and make them the default. Okay, so if you wanted to make the default text size a little smaller, you could do that. You'd save it away as your profile, and from then on, the fonts would be smaller. Yeah, what I've done, and you can see me using it a lot in versions 17, is I've made it easy to change the font size. You don't have to go to graphics options anymore. You can just do it on the toolbar. You know, because you just never know. Some graphs have a lot of text on the right-hand side, some don't. But you could, if you wanted to, change it and save it away. Oh, one other question. I have a question on the power transformation in the capability plot. Data transformed when we adjust the power scroll bar. Can we make sure that the specification limit is transformed to the same power? Oh, it absolutely is. It absolutely is. I guess I didn't make that clear. The questioner says it wouldn't make sense unless we transformed the power, and I absolutely agree. I didn't really say that, but under the covers it's doing that. Here where we did our process capability analysis, you'll remember we had a specification of 220, and I used this to change the power. Okay. Well, under the covers, where it's actually computing CPKs and DPMs and so forth, it is transforming the specification as well using that power transformation, computing the defects per million outside the transformed spec. But then it puts it all back in the original units because that's where I want to see it. Yeah, so yes, absolutely, the spec is transformed before all of these statistics are computed. It's just reversed to put it back on the graph so that you can see it in units of strength and not strength to the -5 power or something like that. So yes, I absolutely agree with the questioner on that one. Okay, well, you've been with me for an hour and a half. I thank you for that. We will be posting again this video as part of our blog, and you can make more comments at www.statgraphics.com. Just look for the button that says Visit Our Blog. Thank you again. I've enjoyed the last hour and a half. I hope you have too. So long.